Thank you. Can you hear me? Okay, good. Yeah, thank you, organizers. Good morning, everybody. Today I'll, as you said, talk about the stability of sedimenting spheres, some work I've done with Rama. Let me begin by just considering a single sphere falling in a fluid that's otherwise at rest. At least in the Stokes regime, it's relatively straightforward to calculate the drag force and thus the terminal velocity. But in the case of two spheres, it's a little bit more interesting. These two spheres will actually, the drag force is reduced and their terminal velocity will be larger. And if they're oriented on some kind of line like this, they will actually drift along this common line. And if we have three spheres, it gets a little bit more interesting. The two outer spheres will be pulled towards the inner sphere and the inner sphere will be pulled down. And the group as a whole will go even faster. And so the question that I'm wondering is what happens when you have a many falling spheres, actually so many that you don't even see the spheres, you just see maybe a cloud like this. And the questions we're interested in are maybe what's the terminal velocity of this cloud or this cluster? Is it stable? Does it stay a blob or does it break apart? And is there any maybe internal circulation of this or are they just sort of static? This has many applications, for example, avalanches or dust storms. I think this is coming off of Africa. Or say this aerosol nasal injection, or inkjet printing, different applications. These are all examples of suspensions. If the main external force is gravity, then we say these particles sediment, or if the particles are more dense than the water, they will sediment, so it's a sedimentation problem. So in this work, what I'd like to discuss is how to develop a simple two-phase continuum model for these sedimenting spheres, and then analyze the stability of different particle distributions. And then compare different structures in 3D versus 1D and 2D. So let me explain what I mean. So these structures can be stable or unstable depending on kind of the geometry. So to be more concrete, let's just say gravity is in the negative z direction, and these spheres are all sort of clusters kind of moving with some average terminal velocity in the direction of gravity. And it's known from the work of Crowley in the 1970s that this one-dimensional chain here of particles where they're all equally spaced. It's actually unstable, so any small kick to this will result in clumps forming. It won't maintain its kind of linear shape here. And similarly, this grid, so kind of a two-dimensional extension here, is also unstable. So any sort of kick perturbation to these particles, it's unstable and it will also form clumps. The clump sizes in these two cases are different depending on particle size, particle separation, viscosity, etc. But what's interesting is that in 3D, so take a sphere of spheres, for example, and let it fall, it's much more stable. It does eventually kind of deform into, say, a torus, but these two clusters here, they actually form clumps quite quickly, whereas this one maintains its shape over quite a longer time scale and actually develops some internal circulation. So I was curious, why is there such a big difference between these kind of dimensionality of these distributions? And in fact, if you kind of take maybe the more natural three-dimensional extension of this, have like a regularly spaced grid, not a sphere, but all 3D space, that's also stable. So it seems like maybe 3D is typically more stable, but we're not sure. So the model we want to use is a continuum description of this. I don't want to actually keep track of the location of all particles. So this is sort of the picture I have in mind. You have some blob of particles, and at the smallest level, you have some fluid parcel, and within it, there's many, many particles, and they have they have their individual velocity, but on average, it'll have some velocity v. Likewise, the fluid could have some very complex, even somewhat swirly, turbulent behavior between the particles, but on average, it's moving with some velocity u. And then in some coarse-grained description, you can write down these four continuum equations, which are basically just conservation laws. So this is conservation of particle number, fluid mass, particle momentum, and fluid momentum. And I'm not making any attempt at this level to specify what the drag force is. It could be a mess, depending on volume fraction, relative velocities, Reynolds numbers, I'm not sure. Similarly, the stress tensor for the fluid could be complicated, and even this fluid here could be some contribution from the particle fluid, particle pressure, fluid pressure, not sure. I've also introduced these as the volume fractions. Okay, this is volume of the particle, Vp. But I don't want to actually solve these. I think this is better left for numerical work. So what I'd like to do is find an idealized model. So let's make some assumptions. let's say the flow is viscosity dominated, so we're in the Stokes regime, basically zero Reynolds number. And the volume of the particles becomes vanishingly small in some limit that the mass of the particles stays fixed. And the particle motion is roughly the same order of magnitude as the fluid. So you don't have like a very slow moving fluid with very fast moving particles at all. Same order of magnitude, roughly, just to get the scaling right. And gravity is of the same order of magnitude as the drag force. And what we end up with is this much simpler system. So we still have a particle number conservation law. We see the drag force, basically u minus v, the velocity difference is a drag force, and that's balancing gravity. The fluid phase is incompressible, and then we have basically a Stokes equation, which is forced by, well, the weight of the fluid itself. This can always be absorbed as a pressure, but the number density of the particles. So it's all, the system should be solved together. The density of the particles influences the flow and the pressure. Flow of the fluid influences the flow of the particles, which then interacts with the density. So it's a big coupled system that should be solved. And at least in noodling around with those complicated equations, I found this is the simplest consistent model that gives sort of non-trivial solutions. If you remove much more, it just becomes too simple. It's weakly nonlinear. There is a small n times v here, so it's not a completely linear system. Maybe a downside is that this drag force here has one remaining unknown, this gamma, which is kind of like reactionary. It depends on the setup. It's sort of like the normal force or tension in classical mechanics. So for example, if you have particles sedimenting in a channel, this would have something to do with the channel geometry. And if you have, like, say, this sphere of spheres sedimenting, would have something to do with, say, the size of this cluster. So this needs to be found somehow. For a single particle, we can back out, at least from dimensions, that it should be related to the fluid viscosity, particle radius, and the mass of the particle. So if it's just a single sphere, this is, I believe, 6 pi, gives the Stokes equation. So let's just apply this real quick to this sphere of spheres. This has a lot of experimental and numerical work to show that it actually remains stable. So you have many, many spheres that together form a spherical cluster, and there's these internal circulations that develop. It's a lot like a droplet of different density, different viscosity falling into this Hills vortex. And this model gives it relatively straightforward. You just solve it like a typical fluids problem. And you can actually see that the particles, at least in this model, do give this convective behavior. And you can actually back out what is the sedimentation speed of the spherical blob. And interestingly, it actually gives the fluid velocity. The fluid velocity and the particle velocity are not necessarily the same. And there's only this similar kind of whirlpool behavior of the fluid for this choice of parameters. Is interesting. I want to think about this more later. But it also gives the instability. So in general, the stability calculations are a little bit involved. Happy to discuss it. It'd be very interesting. But it does reproduce the 1D instability of Crowley. So if you take this 1D chain and you give it a kick, it's unstable. And so at least in Crowley's work, he just did a nearest neighbor calculation. It gives this curve. He did an infinite sum over all the particles, and it gives this curve here. And in the continuum limit, you get this kind of tail curve. So at least for small k, so long wavelength perturbations, it gives very similar behavior. And as expected, for very small perturbations, the continuum model doesn't see the discreteness of the model, so we kind of lose the validity there. But this model should, strictly speaking, just be applied to very large collections. It's sort of a pathological case to apply a continuum model to, but at least it gives something. So then let's take the case of a stratified fluid in the z direction. So what I'm imagining is sort of these layers in the z direction where you have more dense regions, and then you go up a distance L and there's another density region. So it's kind of periodically stratified in the z direction. And what we find is it's actually unstable to any kicks in any direction. So it's unstable, and this is sort of a chart here of XY plane perturbations and Z perturbations. And there's this interesting kind of peak here, or resonance, where the perturbation is exactly at the separation of these large density peaks. On the other hand, if it's horizontally stratified, so say in the X direction, you have these clumps, gravity still acting down, but you have kind of distribution in the X direction. There is a small window here for parameters, for small enough kicks in the X direction where it is stable. And then if you perturb the system with wavelengths longer than these large stratifications, then it becomes unstable. But in general, if we just like take a distribution and kind of perturb it experimentally, or like in nature, it's going to have kind of all wavelengths. It's very hard to like perturb a system with one particular wavelength. So we could say that in general, 3D distributions are actually generically unstable. If you just give it some arbitrary perturbation, it kind of involves all wavelengths. Some of these unstable modes will be activated and the distribution will be unstable. So that basically says something that the sphere of spheres is special when you have this finite collection of spheres forming this sort of toroidal vortex sedimenting. It seems a little bit special, and in the future, I'd like to investigate why is this more stable than these other distributions? And in fact, are there other shapes that are stable? Is, say, the sphere kind of the thing that all things tend to? Say if you take a 1,000 by 1,000 by 1,000 cube of particles and let it sediment, does it want to become a sphere, or is that unstable? Is there something very special about the sphere, or is the sphere sort of like an attractive fixed point? Maybe writing an action principle for the shape of this cluster would be interesting. And in that case, you might call it a cloud. So this could have interesting applications to, say, the atmosphere or cloud dynamics. Okay, I think I'll stop here. I'll take questions. Thank you.
Thanks, Dylan. Questions? Any questions?
Can I ask a question from online?
Yeah, sure. Go ahead.
So Dylan, in the general equation, will it be easy to satisfy the incompressibility of the background fluid? In a reduced Stokes model, divergence of U is 0. But the equation that you showed with all the volume fractions, will it be straightforward to satisfy the incompressibility of the background fluid, or?
Do you mean this?
Yeah.
So here, I don't think if you look at, for example, this equation, I don't think you'd have divergence of U being 0. Like this equation doesn't necessarily say that. If you postulate that from the outside, that say the fluid is incompressible, then this would give an additional constraint. But for example, if you look at one fluid parcel, if your theory is describing these fluid parcels where like in one single cube it's not completely filled with fluid, then we wouldn't actually expect the divergence of the fluid to be 0, if that makes sense. Like as more particles flow into this tiny cube, there can be less fluid there. So in general, I wouldn't expect del dot U to be 0.
I see. So these equations do not limit the interactions. In some way, it's all four-way coupled equations, are they?
Yeah, I believe so. I mean, these are just basically like conservation laws. I haven't specified, at least at this point, what is Tij. This could include interactions, different effects, maybe something from lubrication theory. And even this drag force could be as complicated as you want it to be, depending on volume fraction. Yeah, this is just the simplest thing that I can think of that just is enforcing these conservation laws.
I see. Thank you. Yeah.
So I think in that paper, they consider spheroids, which they say, I think, are unstable. But then for the case of spheres, they say it's stable. And I believe they essentially have a uniform distribution as their kind of mean field. And then they perturb that. And actually in this model, I have the same thing. So if I just take a completely uniform density, then it's stable. It's only once you add, say, like kind of large ripples, large scale stratifications, that it becomes unstable. I'm not sure what they have to say about that, actually.
You can go ahead.
You explained how the one-dimensional arrangement of particles is unstable. Is it still unstable if I make it a circle?
That's a very good question. I want to do that calculation. Yeah, I'm not sure. I suspect yes.
That looks kind of like a sphere, and if you're talking about these
yes
kind of things, that won't affect the circle. So
I think it's unstable. My kind of hypothesis is that what's stabilizing in 3D is the fact that these are able to convect a little bit. Because it's kind of like a smoke ring is a very stable structure. This is kind of, once these start to convect, becomes kind of like a smoke ring. And actually this sphere of spheres wants to deform into a torus. So if you just had a kind of a ring, as it tries to convect, I think it would break apart. I'm not sure.
There are no more questions. Let's thank Dylan.